Everybody, welcome to the February meeting of the Amateur Astronomers Association of Princeton. And we're coming to you live from central New Jersey, not necessarily Princeton, because we do have a snowstorm moving across the east and it's scheduled to drop substantial snow around the Princeton area. So we've elected to go virtual tonight. So no attendance at Peyton Hall. But it's great to have you all here tonight, and we have a pretty exciting program lined up here. I have a few announcements I want to go through and try to get you in the astronomical mood, and then I will turn it over to Victor, who will introduce our guest speaker for the evening. We're very excited about that. We'll take questions and answers after the talk, and then we'll take an intermission of probably 5 minutes and come back and touch on some pretty important things that are happening inside AAAP. You can see them listed there. So we're going to definitely come back to that, and I'll urge you all to stay on board after the intermission. I just wanted to bring up some of the things that are happening in the world of space sciences. And this is one of the latest of the NASA JPL missions that is getting ready to launch. If it stays on target, it's going to launch February 26th or by the end of the month. We don't know that for sure, and they're not listing it, but this is a very interesting project. It will launch on a SpaceX Falcon 9 rocket out of Vandenberg in California, and it will launch the SPEAR-X satellite, which is the spectrophotometer for the history of the universe, which is an astonishing instrument that is going to create a map of the entire sky in greater degree of color resolution than anything that has come before it. 96 different spectral bands in the visible and near infrared. And the data from this is going to feed directly into the JW Webb telescope for target selection and analysis all across the different areas of astrophysics, whether it's deep sky or possible exoplanets. So stay tuned for that. But if you can catch the launch, be aware this is happening in the next couple of weeks. Now, more close to home here, we can look out our windows or go out the back door on these cold winter nights. Everybody's aware that the planets have been an astonishing display over the last month or so, certainly caught the media's attention, and they're still well positioned for observing. I know Dave had a public observing session or members observing session out of the observatory a few weeks back, and I heard that went off really well. Although Saturn is basically setting at sunset now, and Venus is getting close. So you can still catch Venus if you catch it right at sunset. But Jupiter and Mars are very well positioned and astonishingly cool sights, as well as Uranus, which is harder to find unless you have go-to capabilities with your scope. But these are so well positioned. So I just urge you to get out there. This is an image of Io's shadow going across Jupiter's face that I took last winter and had shared with some of the members this image. But I love to show this because it shows the dynamics of our solar system. And what you're looking at here is a composite I created as a video. It is 8 separate individual images of Jupiter, and the rotation is in real time, corresponding to about 2 hours elapsed time total. And you see the shadow of Jupiter's moon Io moving across the face of the cloud bands, coming right over the great red spot. And on the left is Io itself catching the glint of the sun. So this just illustrates how fantastic Jupiter observing is. And you can see a lot of this detail, a shocking amount of this detail, even with an eyepiece. You don't necessarily need to do imaging. So now's your chance. The next month or so is never going to get better than this for at least a year or more. And while you're at it, right between Uranus and Jupiter, and the blue line is the ecliptic, the plane of the planets in our solar system. Right between them and above is the Pleiades cluster. So that would be a spectacular display in your eyepiece. It's a rare sighting to see Jupiter so close to the Pleiades. And I couldn't resist showing you a couple of my latest imaging projects, but coming from our Chilean project, a really beautiful spiral galaxy structure in the constellation in the far southern sky from Chile, one of the NGC galaxy objects, 60 million light years away. And then much closer to home, a nebula in the Large Magellanic Cloud, about, I can't see my label there, 160,000 light years away. So 2 examples of deep sky objects, but one a million times farther away than the other. Well, if you're interested in these kinds of things, I want everybody to be aware, many of you are, but maybe some of you haven't yet heard about our interest group within AAAP, the Astro Imagers group. And we have a pretty close-knit group, and we get together once a month on the fourth Tuesday of the month, and we basically do by Zoom, sharing knowledge and techniques and approaches to doing astrophotography. And if you're not a member and would like to get involved, you can. It's exclusive to AAAP members, but you can send an email expressing your interest to our secretary. You can see the email there, and you can get into this group. And it works through this very clever software system called Groups.io, and we can share images very efficiently and swap messages and information back and forth with Groups.io. A couple of announcements before I hand it over to Victor. We've had some things going on in the club, and we need to acknowledge the incredible work that our treasurer, Michael Mitrano, has been doing for the last 18 years. Yes, 18 years. Michael has informed us of his desire to step down after this really wonderful and beneficial work to the AAAP. So we're looking for a member to volunteer potentially to become the treasurer. This is a board level position, a very important role in the club to keep the books. And we'd be looking for a member, perhaps if someone on this call has experience with QuickBooks or has an accounting background, these would be a real benefit to the position. And so if you think this might be of interest to you to help out the club for a much needed position, send me or any of the board members an email expressing your interest and we can talk about it. We're looking for someone also to become the coordinator of our telescope loaner program. The club over the years, despite our best efforts to resell our telescope collection, it keeps growing, and we have a collection of pretty interesting instruments. They're not huge, they're basically portable instruments, and we want to get these instruments out into the hands of members to start learning how to use and have access to them. And we need someone to take on this role of being the coordinator, setting this up. And again, if you're interested and think you could help the club in this manner, shoot me or one of the board members an email. Now, finally, we talked about this at our board meeting, and I think it's an excellent idea that one of the missing pieces in our outreach effort is ways to do children astronomy sessions, especially out at the observatory. And, you know, we all do this to certain degrees, but really it would be great if we had a person in the club who was a teacher by background, an educator who could help set up a more consistent program of how we can do kid astronomy sessions. And again, shoot me or a board member an email if you're interested in taking on that job. So that's what's going on at this stage. We have more to talk about on club activities after the break, but I think it's high time that I turn it over to you, Victor, and I'll unshare my screen, and there you go. Please take it from here, Victor.
Okay. Let's see. This story for us starts a couple months ago when Aaron Friedman came up to me at a meeting and said, my family and I just had this great tour of the LIGO facility in Hanford, Washington, and the woman docent who gave us the tour was fantastic, and I'm enthusiastic that we should try to get her to do it for the club. So a few phone calls and mostly emails later, here we are. And Kim Burtnyk is the LIGO laboratory technical editor and web content developer, and she's going to give us a virtual tour of LIGO. So
Victor,
yeah.
If you had another screen to share, it's a blank white Zoom screen. It's not something that I think is what you wanted to share.
All right. Well, how does that?
There you go.
There you go.
Oh, nice cat.
All right. Well, okay. I'm
Nice.
illiterate, but there we go. So there's a picture of our guest speaker for this evening. So let's talk about LIGO for just a second. Albert Einstein predicted the existence of gravitational waves in his general theory of relativity around 1915 or so. A century later, the Laser Interferometer Gravitational-wave Observatory, LIGO for short, made the first detection of gravity waves. It was a huge intellectual and financial gamble. and how it paid off big time. The Nobel Prize in Physics, which is often awarded to researchers decades after their epical discoveries, was shared by LIGO's leaders merely 2 years later. Our guest speaker, Kimberly Burtnyk, will take us inside one of this nation's 2 LIGO facilities in Hanford, Washington. The event will begin with a presentation explaining what LIGO is and does, and reviewing some of LIGO's most fascinating discoveries involving black holes and neutron stars. We will then connect with a live view of the LIGO control room, where you will meet one of LIGO's operators who will share what it's like to monitor one of the world's largest and most sensitive measuring devices. Very sensitive, in fact, so sensitive that it can measure the change in distance between 2 masses equivalent to 1/1000th of the diameter of an atomic nucleus, which that's incredible. All right, well, a few words about our guest speaker. Kimberly Burtnyk is the LIGO Laboratory technical editor and writer. She's also a lifelong amateur astronomer who studied astrophysics at the University of Toronto. In graduate school, she conducted a first-of-its-kind study of the impact of observatory visitor centers on the public, researching exhibit design, learning outcomes, and more interestingly, to her, changing attitudes toward an interest in astronomy following a visit to a working observatory. In another life, Kim, maybe that's something we should be talking about later. She and her husband, who also works at LIGO, own a collection of telescopes, and they often bring it out to the LIGO facility for evening star watching activities. So, Kim, thank you very much for being with us, and welcome.
Thank you for having me. This is really exciting. I have to admit, this is my first virtual tour of LIGO. So let's keep our fingers crossed that the technology works for us. I guess I will share my screen and you'll let me know if you see my presentation.
Yes, we can.
Okay. Let me start my slideshow. Okay, here we go. So thanks for the introduction. You covered some of the content that I will have in my slides. So that's good. I can skip over that because there's a lot that I'd like to cover for everyone. I've worked at LIGO for almost 11 years now, actually. So you get a lot of people working here a long time. It's a pretty amazing place to work with, a really amazing group of people to work with. So we're all involved in outreach. A lot of our scientists and engineers and grad students participate on outreach. We all kind of have to help out. We don't have the greatest, the biggest outreach team. So I'm part of that. And so we consider this an outreach event. So let's get started. So you're all amateur astronomers. You know that for 400 plus years now, pretty much everything we've learned about the universe has been through light, electromagnetic radiation. Those are pictures of basically the same region of the Milky Way galaxy taken in different wavelengths of light. And every time we figure out a new way of observing the universe in EM, for example, we learn something new. And big surprise, something was missing, as Victor mentioned, and that was gravitational waves. So a little primer on gravitational waves. What exactly are they? So simply put, they're perturbations in space-time that are made by everything that has mass that accelerates through space. So people, cars, planets, stars, anything like that. Obviously, it's only the largest things moving at the greatest accelerations that we can detect. And that's fine because we're an astronomical observatory, so we're interested in really cool astronomical phenomenon. So some of the things that we are already observing or would like to observe are supernovae, stars that blow up, spinning neutron stars. If a neutron star has kind of a lump on it and it's spinning really quickly, it'll kick off gravitational waves. If it has a star quake and suddenly changes its shape, it'll kick off gravitational waves. It might be accreting matter from a nearby star as well, from a companion star. These are the supernovae and these kind of spinning neutron star class of objects. We haven't observed any of those things yet, but what we have observed are the orbiting pairs of black holes and neutron stars and all of those types of objects. So that's kind of what LIGO, it's really been what we have contributed the most so far to the astronomical community. So as we know, they were predicted in general relativity. GR also claims that they will propagate at the speed of light and will squeeze and stretch space-time as they go, and that's what this little video here is showing. They're also completely unimpeded by matter, which makes them really different from electromagnetic waves that can be absorbed and refracted and reflected, of course. Gravitational waves travel through matter, you and I, everything, completely unimpeded. Of course, this means then, if we could observe these things, we, just like when we observe under using different wavelengths of light, if we could observe gravitational waves, we could learn completely new things about the universe that we hadn't known before. So let's look at at a little bit of the anatomy of a gravitational wave. Let's see out here, we have, let me get my laser pointer, see if that works for us. Okay, do you see my laser pointer?
Yes.
Okay, good. So I'll say in the distant universe, we have a pair of black holes that have been orbiting each other for who knows how long, for millennia. And we know through earlier work that these types of objects are emitting gravitational waves as they orbit, and then they'll collide and they'll send off a really strong pulse of gravitational waves. These are the types of things that LIGO can detect. And so just like a flash of light, the gravitational waves are emitted in all directions. But let's just consider this wave front moving from right to left here. So we'll come back to our squiggly guy here. One way to we always try to figure out how do we explain what this is. So you could say maybe this is a giant blue glowing space tube worm floating out in space. And let's say a gravitational wave passes directly from behind through the center of it. When we talk about this deformation of space-time, you can kind of envision it this way. This is just a way of visualizing the effect that gravitational waves have on space-time itself, the fabric of space itself. So another way to look at this is, say this was a series of satellites organized in rings. And if they were, say, connected in a perfect circle, as a gravitational wave passes, it will cause the circle to kind of squish and compress in one direction and stretch in the opposite direction. And it oscillates back and forth as long as the wave is passing, or as long as the wave is large enough to be detectable. So that means we can really just look at this one ring here. We don't have to look at a whole string of things. So if you look at kind of moments in time, at one moment, the wave as it's passing is kind of compressed and stretched in this direction, and then in that direction, and it oscillates back and forth as the wave passes. And if you notice, what's the common thing here? You know, if we think, maybe we don't need a series of satellites organized in a ring, all we need is kind of this L shape. And it turns out that's really the key, at least for current technology, to detecting gravitational waves. And that's why LIGO is this shape. So what is LIGO? LIGO is an L-shaped gravitational wave detector. The arms are 4 kilometers long. Oh, I will say we are here, we're in this building here. That's where I'm sitting. Emanating from this building are these 2 4-kilometer long vacuum tubes. At 90 degrees to one another. At the end of these arms are mirrors, and we'll get to that in a second. As Victor mentioned, we are the world's largest laser interferometer and I believe the world's most sensitive measuring device. So that's what we are. Now, I'm only at LIGO Hanford Observatory. Here's that nice aerial shot again. We have an identical facility in Livingston, Louisiana. We like to operate in unison. There are some reasons for that in terms of confirming detections. So over time, we've become much better at knowing when we've made a detection with a single instrument. So the second observatory can help with localizing a source on the sky or figuring out where on the sky it came from. But there are two LIGO facilities, so one here in Washington and one in Louisiana. We're 3,002 kilometers apart, which means that since gravitational waves travel at the speed of light, if one were to travel directly in line between our two observatories, the maximum travel time or the maximum difference in time of arrival of the signal at each detector would only be 10 milliseconds. So that was decided deliberately when we were designing the facility. We were always looking for pairs of locations that were this distance apart. And that helps us to kind of eliminate signals that aren't actual signals, but I won't get into that now. We're also part of the LIGO laboratory, which comprises the two detector facilities up here and in Louisiana, and also the universities that really manage the sites. So Caltech and MIT were jointly managed by Caltech and MIT. And a lot of the engineering technology and R&D happens at Caltech and MIT, and then that contributes to our detectors. So let's get to the meat of the matter. How exactly does this L-shaped gravitational wave detector work? Well, first of all, we start with a single laser beam. So again, we're in the same building where I am now, kind of behind a wall that I can show you when we're in the control room. We have our laser room. It's a large laser table. We start with a single laser beam. Here's the mirrors at the end of the arms. We split that laser beam in half with a beam splitter. Each half travels down the arm, and each one travels up and down its arm about 300 times, which effectively makes it like these arms are more like 1,200 kilometers long. We get like the most amount of reach out of this kind of back and forth. It also improves our sensitivity. It stores the power of the laser beam in the arm. And all the information that we get out of the instrument is really encoded in that laser beam. And since the measurements we're making are so small, we need as many photons as possible. So we take a single beam, we split it in half, it bounces back and forth about 300 times, and then we recombine the beams back in this corner area here. We call this the corner station. We send whatever the resulting kind of combined beam to a photodetector, and we look for an interference pattern. And that's basically all we do. It sounds really simple in principle. We are kind of a Michelson interferometer on like the steroids, to say the least. But in principle, that's essentially what we are. And that's why we're called an interferometer. We're looking for and measuring an interference pattern. Okay, so start with a single beam. It splits up, bounces back and forth 300 times. We recombine the beams, and we look for an interference pattern. So I do have a video for those of you who like video. So let's show this. So first thing to remember is that the gravitational waves will squeeze and stretch space-time. So that's this little blue guy up here. Consequently, our arms will also alternately kind of lengthen and shrink in this oscillating, alternating fashion. We use the laser to measure the lengths of the arms at all times. I do want to mention that when we are operating, the laser is on at all times. We don't just turn it on and off. It's just on all the time. So the energy of the laser, the combined laser is coming out all the time as well. But we essentially use the laser to measure and monitor the lengths of the arms at all times. And the characteristic of the emerging laser light, what comes out over here, tells us what actually happened inside the arms. And it just so happens that gravitational waves generate really predictable patterns that come out here, interference patterns. So that's the words. Let me run the video so you can see what I mean. Can I get to the video? I can't seem to, okay. So, oops. I guess I need my pointer, 1 second. Okay, here we go. So there's our single beam that splits up. It's recombined at the corner, and it'll run through this a couple of times, but just so you can see what's happening. Single beam, split into two, travels down the arm, 4 kilometers, hits a mirror at the end, bounces back, does this 300 times, about 300 times, and then we recombine the beams. And then what comes out here, and I'm going to pause it here for a good reason. In this case, the beams from each arm, nothing's happening in the arms, nothing's moving. So the beams from each arm actually totally cancel each other out. So you get total destructive interference. But if something were to happen that were to cause the arms to move, and this is going to be greatly exaggerated. Now, when you look at the output, the beams don't match up so nicely anymore. And sometimes you get total constructive interference. Sometimes you get total destructive interference. And essentially what comes out is a flicker of light. That's what we're really looking for. That's the interference pattern. And as I said, we can predict the nature of, or the type of interference pattern that will come out of the instrument that tells us that it's a gravitational wave that caused that pattern, as opposed to, say, an earthquake or trucks driving by or wind or any number of, weather in the North Atlantic. We can, we're sensitive enough that we can actually detect those types of motions. So that's essentially how we work. And as was mentioned before, using this method, we can measure the change in length of the arm. That's about a couple of thousandth to a couple of thousandths the width of a proton. If we want to look at that in terms of kind of absolute relative change, it's about a change in length, which we call a strain here at LIGO, of about 1 part in 10 to the 22. And put it in terms that I know you will all understand. Oops. It's like measuring the distance to Proxima to Centauri and watching it change by the width of a human hair. That's what 1 part in 10 to the 22 actually means, which is really kind of mind-boggling when you think of it. This is what makes us the world's most sensitive measuring device. So then how do we know when we found something? That's, another question we get from people. We have all this stuff, we're sensitive to all kinds of vibrations, not just gravitational waves. So how do we know when we found a gravitational wave? In really simple terms, again, it's kind of like real-time shape sorting. The first time I learned how we do this, I thought about this toy on the right-hand side here, because I had one of these when I was a kid. And that's kind of a good analogy for how we do this. So as I said, the laser's on all the time. We're constantly monitoring what's happening in the arms. The signal is coming out. This interference pattern is coming out at all times. As that flows out in real time, we send all of that data through what we call a template bank. And that's about 300,000. That's the latest number I have. I think we might have more now, but the latest number that I heard was about 300,000 sample gravitational wave waveforms or patterns. And these are patterns that we've generated over decades using supercomputing resources. And that's because they come from the equations of general relativity. So there are a number of different variables that you can change to make, what would a gravitational wave signal look like from a 30 solar mass black hole merging with a 15 solar mass black hole, at this particular distance, oriented a certain way. There's something like 7 or 8 different variables. And so we've built up this bank of sample shapes of gravitational waves. And we send our data in real time through these templates to look for something that matches. If we see something that resembles a template, then we kind of put a little flag on it. We can look at it a little more closely. We can do kind of an initial rapid verification. That's where it's, close to one of these templates. And then we can go in and kind of modify the template. We tune the template a bit so that it matches the signal. And in so doing, that tells us, what did we have to change? We had to change the mass. We had to change the distance. We had to change the orientation, all of these types of things. And that's how we kind of back out of the signal what exactly it is that we have detected. And then ultimately, we send our alerts to our electromagnetic partners and to the public. There are public websites that you can see where these alerts are coming in kind of in real time. We partner with, I don't know how many at this point. We do have, it's like 150 maybe, electromagnetic regular astronomy partners around the world that get our alerts just in case there's something on the sky that they want to look at. And what's amazing is all of this happens very quickly in a few minutes, a few tens of minutes. So if we look at this toy, then the analog is the ball itself is kind of the whole template bank. Except instead of say 10 shapes, there are 300,000 different shapes. Each shape is one of our template waveforms, and then the yellow blocks here are the segments as they come out of the instrument. So a lot of computing power goes into this, and a ton of data is collected in the process. So that's how we find it. I do have a video that shows you how we can tune the signal. I won't show it now, but if that's something that if you're interested in, it's included in the slide set when I contribute that to your group. So the fun part, what have we actually found? I like starting with this graph. This is called the masses in the stellar graveyard. I have a link to this and other similar charts that you can look at and play with yourself a little bit. First thing to note, this is only our first 3 observing runs. That's what the 01 to 03 means in the heading. And we don't have one of these yet that includes our current observing run, which is 04, which we've been in for almost 2 years now. So that won't be generated until all of the data has kind of been looked at and has been released to the public. We do kind of hold on to our data and our partners for a short amount of time so that those who are part of the larger LIGO scientific collaboration have first dibs on our data. Nevertheless, this graph I find really extraordinary for a few reasons. So let me get my laser pointer again. So these yellowish dots down here and all these red guys, these are all of the known, as of a couple of years ago, all of the known neutron stars and black holes from electromagnetic astronomy, regular astronomy. It took about 50 years to compile this list and to find all of these objects. All of this blue stuff up here, however, is LIGO's discoveries. So let me explain what we're looking at here. Each of these arrows is considered a single gravitational wave event. Each event has 3 blue dots, or in this case, there's some orange and blue, but 3 dots associated with it. The 2 lower ones are the 2 objects that we determined collided and merged into the 3rd one, which is at the top of the arrow. The masses, this is organized by mass of objects, I guess mostly the mass of the combined object. So the masses are on the vertical axis. And when you add all of these things up, all of the EM discoveries, I think there are 106 neutron stars and black holes known to EM astronomers down here. That took 50 years to accumulate that list. LIGO made all of these discoveries, which at the time when this chart was made was 90 gravitational wave events in 25 months of observing. So this just shows just how much more productive LIGO has been at discovering these amazing objects. Down here, the lower one, the orange ones, these are kind of neutron stars, the orange guys. The blue are all black holes. The ones in the middle are things that are in what we call the mass gap. And I will talk about a couple of our discoveries in the mass gap a little bit later. But yeah, this is what LIGO contributed in 25 months. I can tell you as of this morning, I looked, we now have 285 detections. So there would be 285 of these arrows on this chart. I don't know how they're going to make the next one. We might have to break them up by observing run at that point. It's going to get really crowded. Okay, so that's just kind of a nice way of showing what LIGO has accomplished in a pretty short amount of time relative to what EM astronomy has been able to discover of these types of, exotic objects. So current totals, 285 confident detections. We have a lot that are kind of marginal, that we don't consider like our kind of headliners. Of those, 274 have been binary black hole mergers, so two black holes that smashed into each other. And then these kind of range ones are there is some uncertainty with some of these objects, but we think we've had 2 to 3 binary neutron star mergers, 5 to 6 neutron star merging with a black hole, and that includes one that happened just a couple of days ago. And I happened to be actually I was testing the technology for this talk in the control room when that one came in, so that was kind of exciting to be present at the moment that this one came in. We are paying some close attention to this one. And there is some information available to the public. I'll give you links to that at the end of the talk. And then, as I mentioned before, we have 3 or 4 of these mystery mass gap objects. They're mysterious because we don't know if they were black holes or neutron stars, and that's the jury's still out on those. But that's the current state of affairs, including our first 3 and our 4th observing one. So that's everything from 2015. So some highlights. Of course, we start with our very first historic detection. And on the right-hand side here, these pictures show some of the data that we collected. It's kind of the most prominent data. The left column here is the signal as seen by Hanford, Washington. The right side in the blue is how Livingston detected this first event. You see this signal here. This is the squiggly of the, basically showing how the arms were moving kind of up and down, back and forth over this short amount of time. The middle panel here shows some of these templates that I mentioned. So we try to match the template with the signal, and you see we kind of tune things to get a pretty close match. This little third row here is just kind of some of the background noise and residual stuff that that doesn't fit into here, and so we can kind of clean up the signal. And then at the bottom here, you might see some of these in popular press and in media when we have press releases. This is called like a frequency scan, an F scan. We call it that because the vertical scale here is the frequency of the signal, just like frequency of sound, frequency of light. Gravitational waves also change in frequency. And then time on the bottom. So in this case, our first detection was all of 0.2 seconds, the signal as we sensed it in our instruments. And you see that over the course of this, not even 0.2 of a second, the signal goes from, I don't know, 40 or 50 hertz up to 300 hertz, something like that. That's why we call this a chirp. It's just something else you might hear in the media, because over the short amount of time, the frequency of the signal increased from this lower frequency to a higher frequency. So if you were here in person, I would, imitate the chirp for you. I'm not going to do that over Zoom, but I have some links that you can listen to some of those. I think I do. If not, I can send those along. And I want you to kind of pay attention to this because the length of this signal as this was a black hole merger, becomes more relevant in the next slide. So those are the pictures and the words. What was this first detection? It was a 30 solar mass black hole merging with a 36 solar mass black hole. This symbol here, if you don't know, is a sun symbol. So M for mass. This means solar masses. The final mass, which we were able to kind of estimate, was about 63 times the mass of the sun. If you do the math, you notice that 3 solar masses worth of matter vanished. That was turned into this pure gravitational wave energy. And when you look at the power of this event, it amounts to something like 50 times the power of the entire visible universe emitted in those 0.2 seconds. I mean, it's mind-boggling. The distance, people always like to know how far away are these things, was about 440 megaparsecs, or about 1.3 billion light years. Distance is still kind of hard for us to measure, so these are all kind of estimates. So first historic detection, obviously it's the first time that we had successfully detected a black hole merger. It confirmed that binary black holes exist. Astronomers have believed this for the longest time because, something like 50% of the stars in the sky could be at least binary systems, maybe more. Stands to reason then some of those are going to be massive enough to turn into black holes at the end of their lifetimes. Some of those will have two stars that were massive enough to turn into black holes at the ends of their lifetimes. So there was always this presumption that there was a population of black holes orbiting one another. And so we did confirm that those exist. I will say that there was a discovery, an indirect detection of gravitational waves in the 1970s, Hulse and Taylor. They both also won the Nobel Prize for that work, but that was kind of using mathematical methods. They looked at the orbital decay of a system and realized over time that as these objects move closer to one another, they could explain the change in their orbit by these things emitting gravitational waves. So there was, really strong evidence of gravitational waves decades ago. What LIGO did was the first instrument to actually physically sense the change in space-time itself. And we confirmed that black holes can smash into each other. And of course, that LIGO works. LIGO has a very long history. We started, the grant for this was submitted to the National Science Foundation in 1990, 89, 90, 91. So it's taken a long time to get to where we are. And this happened in 2015 was our first detection. So what I consider our most scientifically rich detection was a binary neutron star merger that happened on August 17th of 2017. And I mentioned in the previous slide to pay attention to the signal here, because I also mentioned that gravitational waves give off kind of signature signals depending on the nature of the system that's generating the wave. So each thing is kind of like a fingerprint. This is a beautiful way of illustrating the difference between, in this case, two neutron stars merging. In this event, the neutron star merger, the signal is noticeable in our detectors for about 100 seconds. So you compare that to 0.2 seconds for a black hole merger. And so right here, I took that picture on the previous slide and I squished it so that it's about the scale of 0.2 seconds on the scale of the neutron star merger, just to show how different these types of signals can actually be. So the reason for this is neutron stars are less massive. And so LIGO has kind of a sensitivity range, just like we have a hearing range. It's sensitive, in a certain range of frequencies. And so these objects, neutron stars, black holes, have been orbiting each other for millennia. It's only when they start to orbit each other and give off gravitational waves that fall within our detection range. I'm going to use hearing range, even though we know we don't hear in space. It's only when they reach that point that we have the potential of picking up these signals. And then, of course, these things then are moving much faster, and they're orbiting each other much more quickly. So the neutron stars kind of spend more time in our sensitivity and our sensitive range because they're less massive. It takes them a little bit longer to merge than the black holes. The black holes get to that point and then merge very quickly. So a lot of this is based on the mass of the objects. In this case, the neutron star merger, there was a 1.5 solar mass neutron star that merged with a 1.3 solar mass neutron star. And it was pretty close, only about 130 million light years away. When we get in the control room, I'll show you a graph of our range that shows us how sensitive we are based on how far away we could detect a neutron star merger. And I'll talk more about that when we're in the control room. Black holes, obviously, we can detect much farther away. They're much more powerful events when black holes are colliding. So that's just kind of the first interesting thing of this event. I think, especially for this group, what's more interesting, it was also our first multi-messenger event, which means that it's the first and so far only time that this merger, a gravitational wave event, was also detected in electromagnetic wavelengths. And in this case, it was gamma rays. So LIGO made this detection, this kind of chirp of the gravitational wave, and 1.7 seconds later, 2 orbiting gamma ray observatories reported a gamma ray burst, a short gamma ray burst. And like I said, since we share a lot of our information with astronomy partners, people paid very close attention to this event. And each of us can make kind of a sky map, roughly where on the sky these events were coming from. And when we combined all of our data, so it was LIGO and Virgo, which is a facility in Italy, they were observing at the time as well. Similar to ours, they're a little bit smaller than us. They made a sky map, LIGO made a sky map, the Fermi and Integral made sky maps, and this was the result. So this big blue swath here was as good as Fermi could do, or sorry, Integral could do. The blue blob was the Fermi sky map. And then LIGO was this kind of light green banana shape. And when we also included the Virgo sky map, we overlaid everything, and this little region of sky is where everything intersected. So that got all the astronomers really excited. It amounted to about 30 square degrees. There were about 50 visible galaxies in that region. Unfortunately, it was still in daylight when this occurred. So, and it's in this it's in Hydra. It's really from the northern hemisphere. It's really, really, really low in the sky. But the SWOPE telescope in Chile, they were on it as soon as the sun set, and they basically systematically imaged every galaxy that was in this region and compared it with previous images, which I find amazing that pretty much every visible galaxy has been imaged multiple times. And so on the right-hand side of this map panel, the lower one is an image taken, I don't know which observatory this was, but this was taken about 3 weeks before the event. And then here's the SWOPE image about 11 hours after, and you clearly see what looks like a supernova. We refer to this actually as a kilonova because these events are about 1,000 times brighter than a supernova. And this is a really beautiful HST image of that galaxy with the kilonova in the box here. So my husband and I did take our 22-inch Dob out one night, and we did see this galaxy. This was after the detection. We did see this galaxy visually through that telescope. It was incredibly challenging. It's probably one of the most difficult things that I've ever seen. Really, really low on the horizon, but we did spot it from the parking lot. So that was kind of a fun thing. So yeah, it was the first time that a source of gravitational waves had also been very precisely localized. It quickly, as a result, became the most studied astronomical event in human history that we're aware of. About 30% of the world's professional astronomers were on this object as soon as possible. It solved, I'll say solved the mystery of short gamma ray bursts. You know, we can never be sure that every gamma ray burst is caused by this type of event, but nobody really knew what they were. There had been speculation that it would be this type of, neutron star merger. And we could at least confirm that that speculation is correct. There may be other sources, but certainly one source of short gamma ray burst is merging neutron stars. It was another way of measuring the Hubble constant. Since we had an optical counterpart to the gravitational wave, we could use gravitational waves to kind of measure the Hubble constant. I don't know the details of that, but I do know that the results are consistent with the current electromagnetic based estimates, which also range depending on who you talk to. Another big thing was it definitely confirmed that gravitational waves travel at the speed of light, which was a prediction from general relativity. And we have a nice little kind of video clip over here of this object fading. Obviously, it moved from gamma rays into optical regions and then out pretty quickly in the matter of a couple of weeks. It was observed in radio for months afterward. And that's what really helped us to extract a lot more information from this particularly extraordinary event. And I think that's on the next slide. Yes, so I think, to me, this was the biggest boon from this event was it really transformed what we know about the periodic table. So when I was studying, astronomy, astrophysics, I was told, oh, everything over iron has to come from supernovae. Turned out that was a lie because all of the things here that you see in yellow, we now know come from merging neutron stars. And that's all because of this one event. So historically, we see a lot of these heavy elements on Earth, maybe in other nebulae and things like that. But when we look at the abundances of these objects, and then we look at, say, what supernovae are generating, either we don't see them at all, or we don't see enough of this stuff being generated with supernova to account for how much we actually observe in the universe. So when the astronomers studied the aftermath of this neutron star merger, this is what they found: copious amounts of these heavy, heavy elements in the periodic table. So let's see, some numbers: 16,000 Earth's worth. This is a symbol for the Earth, M Earth. 16,000 Earth masses worth of heavy elements, all this yellow stuff, were formed, including, some people like to know this, about 10 times the mass of the Earth worth of gold and platinum. But this was really an extraordinary discovery. Now we know at least some, one source of these types of materials has to be emerging neutron stars. Okay, a couple other things moving away from that, just some little tidbits. We've seen some really big black holes in gravitational waves. There's another class of black holes called intermediate mass black holes. And they're between 65 and 135, ballpark solar masses that stellar astrophysics claims cannot form through supernova. You can't make a single star big enough to make a black hole of these masses at the end of its life. So how do these things form? We have two events that kind of give us some clues that the larger component masses are formed by previous black hole mergers. So here's some, this is April 26th of 2019. We had a 105 solar mass black hole merging with a 76 solar mass black hole. They're already kind of in this intermediate range. There's one that was a little bit smaller, the 98 and 57. And I think that's this guy. Oh yeah, this guy here. So the two that I point at are kind of the interesting ones, where we have these lower mass ones that could be stellar. They're generating these larger ones that can't be stellar. So it does suggest that when we see these kind of intermediate mass black holes in the universe, that they were formed by previous mergers of black holes. This asterisk here is what I was talking about, the distances being difficult to measure. I wanted to, reliable distance that we get is in redshift. Not everybody kind of knows what that means in so-called practical terms. So I did make an attempt to convert that very roughly into light years. There's a little link here that you can look at to kind of make those calculations yourself. It really depends on a lot of factors, depending on how you interpret, the Hubble constant and the nature of the universe itself. But there are some extra slides at the end of my talk that, you will have that you can look at. Things like look back time is maybe a better way of looking at it. But yeah, roughly, we're getting farther and farther into the depths of the universe here with some of our discoveries. So that's kind of an interesting contribution we've made to astrophysics, is what are these intermediate mass black holes? And then I think this is the last of our discovery slides. There are these mystery objects in the mass gap. These are really interesting because here's our mass gap again, between about 2.5 and 5 times the mass of the sun. We're starting to see objects in here, but we don't know, are they the lightest types of black holes we've ever seen, or are they heavy neutron stars? So again, stellar astrophysics hasn't really caught up to understanding how objects in these masses could be made. So hopefully we are starting to make some contributions to that. They've only been seen in gravitational waves. So this is why we don't know if they were, if this was a neutron star or a black hole. We haven't actually observed one of these electromagnetically yet to really determine what they were. Also kind of curious, we had the most asymmetric system observed with a 23 solar mass black hole merging with this 2.6 solar mass mystery object, probably a neutron star. It's kind of at the low end of the mass gap. And kind of coincidentally enough, the most symmetric system that we have observed with definitely a neutron star at 1.4 solar masses merging with this very mysterious 3.6 solar mass object. It's kind of squarely in the depths of the mass gap here. There was a paper written up about this, and this was only 2 years ago. This was in our current observing run that we made this discovery. And again, the distance is in, under 1 billion light years, pretty low redshifts. This one's really close. So let's see, is that it? So let's see, ways to stay tuned then. If you would like to know more, we do have some catalogs available online that you can look at yourself. There's the Gravitational Wave Candidate Event Database, GRACE-DB. Here you see this is that February 6th event. I grabbed the screenshot of that one for you. This is what the screen kind of looks like when you look at the events. We also have something called GWASC, the Gravitational Wave Open Science Center, that is available to the public. Gives you a little bit more data, but they're just kind of fun things. These are both updated as soon as we have a detection. Like this one came up, I don't know, 10, 15 minutes after it happened, it appeared on this website. So these are all available to the public. We withhold some of the details of our discoveries for our astronomy partners and for the people who kind of have first access to the data to kind of analyze and write papers on it. But we do release a good amount of information to the public right away. And in fact, you can get, if you have an iPhone, you can get alerts on your phone as they happen. There is an Android app. They're currently under redevelopment, so I didn't use that link right now because I didn't want people to go there and realize, wait, I can't use it. But if you go to our website, the ligo.caltech.edu, you can find it there. I think even there I have a note that says it's under development, but we're just waiting for them to finish that for Android use. We have these interactive plots, the mass plot, the masses in the stellar graveyard plot that I showed you. You can kind of manipulate those and look at them in different ways and kind of sort them in different ways and organize them in different ways. We have things called bubble plots that are made by Cardiff. That's these green guys up here, and they're just kind of fun to play with. The sky maps. Cardiff makes these absolutely beautiful sky maps that show you the regions on the sky where the gravitational waves events are coming from. This is just one example where you can see they're not very well localized. We need at least 2 detectors to get reasonable localization. 3 is better. The more we have, the better. There are other detectors around the world that we, well, there's really only 3 right now that are operating at kind of the level that we are. So we're hoping that some more in the next 10 or 15 years will come online and we'll be able to really pinpoint the sources of these things. And hopefully then our astronomy partners, our EM partners, will be able to observe more of these things with telescopes. Of course, there's always YouTube links. There's a LIGO Virgo Kagra channel. Max Planck Institute does some really, really nice animations and kind of illustrations of gravitational wave physics. And the SXS collaboration makes these beautiful orreries. They're like digital orreries of our detections. And they're just kind of fun to look at. And they're just short little clips where you can see the different masses and kind of how quickly they're emerging. And of course, if you have additional questions that I can't answer now, yeah, please feel free to reach out, and we are more than happy to answer questions for anyone at any time. So I think that's it for me. That was kind of whirlwind because I do want to get you into the control room. Should I stop screen sharing? What do you think?
I would say probably yes.
Okay, screen stop share. Okay, phew, that was a lot.
Good job.
So yeah, questions. You may have some questions.
Do you want to take
Why don't
questions
you
now?
unmute yourself to ask a question?
I have a question.
Sure, we can do some now.
Yeah, so the orientation of the L shape it affects what direction you can detect things from.
Yes.
Much effort was put into the orientation of that on the surface of the planet here.
There was some, first of all, we have to deal with the curvature of the Earth. So that kind of gives us a little bit of variation, which helps us to kind of, get a little bit more information out of it. There was some consideration about like the polarization, whether or not gravitational waves are polarized and if they could orient things in a different way. I don't think that was done with these detectors, not deliberately. I could be wrong, but I'm pretty sure other people have asked that question, and I don't think that was something that was ultimately worked into the orientation on the Earth at this point. There's the Virgo detector, which is the 3-kilometer interferometer in Italy. So they're oriented in a slightly different way. They're not as sensitive as us. They're only about, I can show you in the control room, maybe a quarter as sensitive as us. But they were absolutely fundamental and instrumental in us detecting the neutron star merger. So yeah, we have the 3, can help us localize things a little bit better. But yeah, the whole polarization question, I don't think we've really tackled that yet.
Kim, I have a question.
Yeah.
The gravitational waves themselves have wide range of frequencies, right? Starting
Yes.
from the low end to the high end.
Yes.
And I think the LIGO is only sensitive to a certain frequency range. So is it being enhanced, or like are there any measures to detect other frequencies of the gravitational waves?
Within LIGO, so LIGO was deliberately designed to kind of detect gravitational waves that were most well understood from theoretical perspective. And so when we get in the control room, I can kind of show you a picture of our frequency range, or we call our noise spectrum. Now, having said that, yeah, we do have this kind of limited range, low and high. It's really centered on the sweet spot of black hole mergers. But we are also always trying to kind of eliminate as much noise. Noise to us is any vibration in the interferometer that is not caused by a gravitational wave is noise to us. And so we're always trying to eliminate the noise. And what that does is it kind of pushes down the floor of the, it improves our sensitivity. And we can also we're using something technology now called quantum squeezing. Don't ask. If there's someone out there who's, familiar with squeezing and laser technology, you can write about that for folks. But that enables us to kind of, I'll say, flatten this curve. Right now, it's kind of a good scoop, and I'll show you in the control room. We're able to kind of flatten that a little bit, which then gives us a little bit more sensitivity at the low and the high ranges of the detector. It doesn't expand our sensitivity, but it does kind of give us access to what is on the fringes of our sensitivity ranges. Does that answer your question? There is, plans for LISA, which is the orbiting, not orbiting, it's a space-based detector, which will have a slightly different range of sensitivity.
I had a question, Kim. The thing that really surprised me in your presentation was that we can get heavy elements out of 2 colliding neutron stars.
Yeah. How
does that happen?
We had a really great presentation from a guy here who's like a nuclear physicist type. He talked about our process thing. I'm not in nuclear, physics. He did mention kind of the processes, but I think ultimately, what little that I know from, watching NOVA and things like that, these heavy elements, what do they have in common? They have a lot of neutrons in their nuclei. There's a lot of protons, you need a lot of neutrons. Seems to suggest to make these things, you need a lot of neutrons to smash together. So that might be why, historically, the physics community figured that maybe that's where these things come from. And in hindsight, it almost kind of seems obvious that, oh, okay, you smash these big giant balls of neutrons, together, and through these nuclear processes that you're going to get these copious amounts of heavy elements. It was really amazing what they discovered after that. But the actual mechanism, yeah, I don't know what the kind of nuclear mechanism is that generates these things.
Yeah, that's what I'm wondering about. There must be some, energy that's causing neutrons to turn into protons and electrons.
Yeah, well, there's just the compression of these things, at the moment of their collision. You get the radiation that's coming out of it. That's the artifact of whatever nuclear processes are happening with the matter itself that generate these heavy elements. But yeah, that's a good question.
One question on that. I think I missed an important point. How do we know that the heavy metals are created in the neutron star collisions? What was the role of gravitational waves in that?
Okay, so when we were able to localize the source, so we knew then LIGO made this detection. We said these are neutron stars merging together. The gamma ray facilities, saw the gamma rays. We localized the source, and then the electromagnetic astronomers looked at the aftermath of this collision, and looking at the nebula, the cloud of material, just using spectroscopy, which we can do from ground-based observatories, they could see these elements in this kind of cloud aftermath of this event.
Oh, from spectra?
Yes. Yep.
Oh, okay. So it's really the correlation between gravitational waves saying it was neutron stars and light astronomy saying there is these elements.
Absolutely. Yep.
Thank you.
Yep.
Oh, one other very simple question. What is the actual sort of raw data rate from the machine?
Oh, that's a good question. I should know this because this is my husband's thing. He manages the computer cluster here. So, oh Lord, I'm not going to know off the top of my head. Wait, is there anyone? Dave, you're not here, are you? No, except for someone here who does computing stuff. I don't know, or like a couple of a couple of petabytes a year. It may not be as much. I think the data itself isn't that complex. I'm probably spewing all kinds of lies right now, but I might, if you're interested, I can get back to you on that, on the details, if that's something you're interested in, for sure.
I just got the impression it's really you sort of getting a single waveform out of the machine like you were showing in the graphs, or is there really much more to it?
It's just that it's all coming out at the same time. And we also have to extract, I mean, there's a lot of data in that signal. There's possibly gravitational wave signals, but then there's just, the random noise. LIGO's, the instrument is sensitive enough that we are at the level where we now have to deal with the quantum effects of the laser beam itself. We can sense the Brownian motion of the coatings on the mirrors, just the random motions of molecules that we're sensitive enough. And that's noise to us. We want to eliminate as much of that as possible because the gravitational wave signals are so much smaller than those things. So all of that is coming out of the instrument and is part of the data that's coming out. And so, it's not just a nice, quiet or gravitational wavy waveform. There's all this mess coming out that needs to be kind of handled. And we save all of this data. We have data back to the 25-year-old data. We are still saving it on tape. It's backed up in multiple places. I think we're moving to more like solid state technology, but for the time being, people still access our data on tape.
Okay, thanks a lot.
Sure.
Around the time that LIGO was being invented, there were other competing gravitational wave detectors that were being considered. And one of them was, I think it was a 2-ton cylinder of superconducting niobium that resonated and under the effect of gravitational waves, and that resonance could be detected mechanically and transduced into an electrical signal. And it was orders of magnitude less sensitive than the LIGO interferometer, but was also orders of magnitude less expensive. Are there any efforts to produce lower sensitivity gravitational wave detectors that are more affordable and could be dispersed over the world, kind of like the citizen scientists of the gravitational wave world?
I think some of these bar detectors are still in use in places, but you know, given what LIGO had to do to make the first detection of something that was a pretty strong signal, I don't think it's the kind of thing where, you know, it's not like VLBI, the long baseline interferometry, where you can have a bunch of different radio telescopes around the world and you make one big telescope. I don't think it works like that because each individual detector has to be sensitive enough to make a detection on its own. I could be wrong. It's not something that people have really, that I've heard people talk about. But my sense working here and knowing we have one of the original Weber bars on display here, actually, in our, which is one of these bar detectors similar to what you're discussing. Weber believed he made a detection. It could never be verified. There's still some debate over that. I think most people think he didn't actually. When we talk about that, when we have visitors coming, though, we consider that a positive thing because it really kind of spurred the technology and like what is required to detect these crazy things. And in terms of cost, LIGO has spent, we've been given about $1 billion over 25 years. So I did the math recently. It comes out to something like 10 cents a person per year or something like that. If you consider 300 million people in the US or 200 million taxpayers or something like that. So it sounds like a lot, you know, in one lump sum, but when we spread that out over a couple of decades. I will say, though, it was also the largest or most expensive single project that the National Science Foundation has funded. And for sure, this would never happen again. You know, for one, science has become more expensive and it's more complex. And so moving forward, there's going to be a lot more, you know, international engagement and cooperation and funding coming from different sources. So we might have just kind of snuck in as the last big project like this that would be funded by any single entity, understandably.
Thanks.
Real quick one, what would the signal look like if you were to detect a merger event that was only, say, 1,000 light years away or 100 light years away? How would that compare to what you showed?
Oh, that's a good question. You know, the kind of the pretty blue and yellow and green F-scan, our first detection was pretty noticeable in that. It's not often that you can actually see that in that type of graph or scan. I don't know, you know, it would depend on the obviously the nature of the objects that are emerging. I don't think I'd want to be that close to one of these things. It might break the instrument because it's that sensitive. But yeah, that's a question for Ray Weiss. I know other people have asked Ray Weiss. He's one of our founders. You know, how close would you have to be to a gravitational wave for it to ring your eardrum enough that you would actually, you know, oscillate your eardrum enough that you would actually hear it? And it's pretty close, although he did say you know, you wouldn't want to be there. I was going to say something else about that. I've forgotten now. Yeah, I can't think of that. But you know, one thing I did think of with the neutron star merger was, given the aftermath of that thing, you know, you wouldn't want to be anywhere near that thing happening, as, you know, planetarily wise. And I've wanted to ask the question of some of our astronomers, you know, how far away is a safe zone from something like that happening? You know, thankfully, we don't see any objects like that near to us in our galaxy, so I don't think we have to worry about that. But it would rattle things up here for sure.
I have one question. So going back to your sine waves, and so we got a sine wave which depends on the wavelength of the laser, and then because we have two beams and they're shifting because of the gravity wave jiggling the the distance. How many wavelength, and this is going back and forth a few hundred times, you said.
Yeah.
What's the total wavelength shift of that couple hundred reflections?
I'm not sure I understand. You mean of the laser beam itself?
Yeah, I mean,
or-
the waves are jiggling back, relative to each other because of the motion. And, it could just be moving a half of a wavelength back and forth, or it could be moving 6 wavelengths back and
Oh,
forth.
right. You're right. I think it depends on the signal, and not only on the nature of the objects that are making the signal, but also the direction. So we each have blind spots as well.
Yeah.
So there's kind of an optimal direction if the gravitational wave, I think if it's coming directly, down on top of us, that gives us the biggest effect. If it's coming along one arm, then the way that the wave actually manipulates space-time itself, limits what we can detect. And in fact, Virgo's contribution to the neutron star merger was the event was loud enough for Virgo to have seen it, and they were operating, but they didn't. And so people were wondering what's going on. So we looked at Virgo's blind spot map, and it fits squarely in one of their blind spots. And without that kind of blind spot really narrowing down where on the sky it came, we probably, if Virgo hadn't been observing, we wouldn't have detected it. So even though Virgo did not sense this thing, it was absolutely crucial in localizing that particular source. So yeah, complicated way of answering your question. It depends on, the nature of the source, the direction that the waves are coming in, and how much the arms are moving. So it could be a fraction, like you said, a fraction of a wavelength to, I don't think it's more than one wavelength. I don't know. I don't want to say because I don't want to mislead you, but
it's not 100 wavelengths.
But
No.
it seems like if you have 1,200 meters in your path, which is 4 times 300, and it's a half a nanometer wavelength, just guessing, that's 10 to the minus 14 is the ratio of a wavelength to the path, and you're down, your noise level is 10 to the minus 18. That suggests roughly a 10,000th of a wavelength that you're sensitive to, which is pretty amazing.
Yeah,
Amazing.
sounds good
That
to
is
me.
really
Yeah.
amazing.
Yeah.
And,
Yeah, it's a little mind-boggling that we can pull
It
this
is
off.
mind-boggling. It for
Yeah.
sure is.
and none of these 285 or so events observed so far have happened in our galaxy Milky Way, right? Everything beyond our galaxy.
Everything, yep, far. I think the cosest one maybe was our neutron star merger, and that was 130 million light years away in a not too distant galaxy, cosmologically speaking.
Fortunately for us.
Yes, exactly.
Hello, Kim, can you hear me?
Yes,
hi. I just wanted to, prior to LIGO making its first detection, we had we assumed theoretically that there were black holes all over the place, but how many prior to its being turned on did we actually confirm? Is it just the one black hole in our own galaxy that we actually had confirmation of, and the rest were theoretical?
Oh no, we've observed, astronomers have observed or detected, I don't think the word observe is the right word for it, black holes, I think often in, pairs of systems. So you'll have, like Cygnus X1 is, I think, a classic example, where there's a X-ray source, there's 2 objects, or there's one object that's kind of orbiting, they don't see the other object. The one object is, something's emitting X-ray sources, they don't see it, but looking at the properties of, like the orbital properties, they can determine the masses of the 2 things that are orbiting. And so one they see and one they don't, and they look at the mass and they determine that was a black hole. So there have been, I think that chart that I showed, the masses in the stellar graveyard, all the red dots were stellar mass black holes determined or discovered by electromagnetic astronomers. And then, as you were getting at, we know that, most, if not all, galaxies, at least spiral galaxies, have supermassive black holes at their centers. So there's 2 different classes of things too.
but in terms of direct observation, the numbers would be relatively small compared to what the LIGO is picking up.
Yeah, absolutely. I think, I could go back to that slide. I don't want to go back to that one. It's maybe, actually, I can shrink this and go on my own. The masses in the stellar graveyard, I don't know, it's maybe like 20 black holes. I didn't mean to actually look this up and see how many do we actually know from electromagnetic astronomy. So it's funny that you asked that question, because a couple days ago I was thinking, I wonder how many we actually, like, what's the actual number? It's not a lot. It's certainly we know a lot more neutron stars because we can see neutron stars, and pulsars are neutron stars. So yeah, LIGO has kind of blown all of those black hole discoveries.
On a separate issue, just from the engineering side of it, do you have an image of the mirrors? That's what got me excited, was how you guys built these insane stable mirrors.
Let me look through might have a extra mirror. Let's see. I do. So let me.
Also, I should note, we might want to let Kim get through this so we could do the tour.
Yeah, I think that's a good idea.
All right. Can I send you, is anyone else interested in seeing a picture of the suspension?
Oh, I'm definitely interested. That's a big
Okay.
area. Yes, that's very interesting, I should
So
say.
If you want to share it, Kim, you could.
I'm gonna try and, okay, here we go. Do you see that?
Yes.
Okay, so this is, here's a schematic. Is this full screen for you? It's not for me.
No, it's not.
Okay, let me try and. I've got the Zoom, bar overlooking everything. Okay, and
Go to the slide.
okay, there we go.
Yeah, there we go. Yes.
So the schematic is kind of a diagram. This is the thing that now resides at the Smithsonian that I really wish we didn't give up. It's called this quad suspension. This is kind of a diagram. The lower mass here, which equates to this pink thing here, it has a cover on it. That's why it looks that color. This is basically the mirror that the laser beam reflects off of. There is 100 million times, a factor of 100 million vibration damping between the top of this device and this mirror. So that's kind of another excruciatingly extreme number that we throw around LIGO. So this shows just kind of this bottom portion, maybe a little bit of this segment here. I don't have one that shows just the mirror. The mirrors are these beautiful, they're made of pure silica, fused silica material. They're suspended by fused silica glass fibers that are 0.5 millimeter in diameter. Each mirror weighs about 40 kilograms. I shouldn't say about, I think it's very precisely measured. And so that's the part that reflects the laser beam. We want this mirror to feel like it's floating in space. Everything we do, eliminating noise, making this mirror not feel any terrestrial vibration whatsoever. So we're limited in how well we can do that. But we're doing well enough that we can actually detect gravitational waves now.
That's mind-blowing.
It is, yeah. Okay, let me walk over. I'm gonna unplug the speaker that I have right now. So I'm gonna have to transfer to I think the camera speaker will take over. So give me a moment to take care of that. Okay, so this is the LIGO Hanford Observatory control room. We'll do a little panorama here. Nothing exciting up there. Here's where all the action is. It's pretty quiet now. It's after hours for most folks. This is our operator station here. This is Ibrahim and Ollie, who are working to, when do you guys get off work? 6:30? Well, no, Ibrahim's on till 10.
Yeah.
And Ollie?
I'm here till 7.
Till 7. Okay. So this is where when we're in an observing mode, there is somebody, an operator on duty 24 hours a day. And so we have it now that overnight, the light shift, they can do this from home and monitor things remotely. It used to be that they had to be in this chair, we call it in the chair, between, midnight and 8 a.m. Thankfully, they don't have to do that anymore. So Ibrahim, you want to tell us what you do as an operator?
Yeah, for sure. So I am the current LIGO handheld operator on duty. So the operator's job is sort of twofold, very broadly twofold. The first and most important job is to keep the interferometer locked. I'm sure you guys got some background as to what locked means, but to go very brief into it, it just means that the entire interferometer is in like resonance, or is in like a resonant cavity where everything is sort of in phase. The laser circulation is very much like in phase with itself in order to be able to catch only the most sensitive interferences. And then the second sort of job is to coordinate the site activities with everyone here. So if someone really urgently wanted to go into like one of the labs, it's the operator's duty to tell them yes, no, why, to ask questions, and to basically like put that onto the reservation system. On Tuesdays, today is Tuesday maintenance, where we intentionally down the interferometer to go into the laser vacuum enclosure area, also known as the LVA, to do so that's the operator part of the job. And as you can see, there's so many screens that are involved with the first part of the job, which is keeping the interferometer locked and monitoring its current like behavior. And then there's one half a screen dedicated to the coordination of who is where. Right now, there's no one anywhere. Thankfully, because it's
late. Yeah.
Yes, but yeah, that's kind of the very brief job. I'm down to go into more specifics or take questions.
Okay. Any questions for Ibrahim at this point? I can show you some screens.
Yeah.
I see the clock on the up above. What's the other time? This says 2 something.
Ah, the clocks. Yes.
Oh, yeah.
Let me walk over here. We'll get a closer view of these. So 2 clocks. The one on the left is universal time, 2:05. The other red one is our local time. And any guesses? Okay, I'm giving it away. Any guesses what this green thing is? It's a common question we get here when we bring people to the control room.
It's probably some kind of Star Trek-y thing.
It is a clock. There's a hint.
Looks like it's counting seconds.
It is counting seconds.
Number of seconds since startup?
Close. This is GPS time. Oh. So we coordinate our detections between the sites by using GPS time. We don't obviously rely on local time zones, etc. So this is the number of seconds that have elapsed since, I always get this wrong, January 1980, when the GPS systems were first initiated. And so we timestamp our detections based on GPS time so that we can compare things more readily. So while I'm over here, talked about some noise. This top chart here, you probably can't read it. I'll read it for you. It says earthquakes in wind tilting buildings. So this just shows us over the last 24 hours. So on the far right hand side is current time, and then to the left is the last over the last 24 hours. So this is a way that we can look at earthquakes. We can't predict earthquakes. Some people ask, can we predict earthquakes? We are as susceptible to earthquakes as anyone else, but we need to know about them so that say there's some big earthquake in Indonesia that we have 20 minutes to prepare for. If it's really big, the operator can put the instrument in like a safe state to protect the optics and the laser and all of that kind of thing. But yeah, not a lot. I think I'm guessing the last, the stuff that's like 8 or 10 hours ago is stuff that was happening locally on site because it was our maintenance day. The one below that, it says wave-driven microseismic peak. That's kind of like a weather. We can detect the weather patterns, like oceanic weather patterns. if there are, low or high pressure systems, it causes the ocean, the full like column of water on the ocean and the coastlines to kind of vibrate. And that sends that vibration through the crust of the earth. And that's something that we can sense here. So that's what that lower one is showing. So these, again, are ways that we can kind of look at what's the noise over the last 24 hours. Questions?
So Kim, you call these sort of artifacts, I guess, noise, but if I were a seismologist, would I find these interesting?
Not so much. Well, I don't know. We have seismometers around the site that provide us with the seismic data that we need to kind of extract or remove from our signals. I don't know if there, I don't know. Has anybody ever asked that question? Is any seismologist been interested in like the microseismic data or anything like that?
So recently, not seismologists per se interested in the microseismic data, but I heard the staff scientist at one point a few months ago talk about how the data from the BRS, which is the beam rotation sensor, would potentially be useful in like a research environment. Basically, like it's sort of like a converging evolution thing where the best seismometers are always eventually interferometers. And so I would say, yeah. And so I don't think anyone's asked for any of the data, but I do think definitely because this is one of the areas where it's monitored the most, it would be to some extent useful, though I don't know how specific the data could be.
Yeah.
It's mostly for the purpose of attenuating any seismic sort of signal. So we have everything like tuned to that.
Yeah.
And there's not much else that we can sort of control to do anything else with it.
Yeah.
So it's really just the data itself, other than experiments. But yeah.
Yeah, not an uncommon question that people ask about, our relationship to seismic data and what that does for us. I mentioned the noise curve and kind of our sensitivity range and what that means. This is what we're looking at here. So this red thing, and I can provide links where you can see, I think it's available to the public. I'll have to double check that. Where you can see some of these screens kind of in real time if you just wanted to log in on your own. But this shows kind of the low end, 10 hertz up to 1,000, a couple of thousand hertz. That's kind of our main sensitivity range. And you see it's kind of this curve shape. That's what I was talking about, how it's kind of got this bowl shape. And with the magic of the squeezing that I very, very loosely touched on, we can flatten that curve a little bit so that at the low end, we can be more sensitive. The high end, we can be more sensitive. But our sweet spot is right in the middle where the lowest, you're just looking at that red line. Our goal is to push that red line as, far down that graph as we can. There are some other features in there that are things called violin modes. So the glass fibers that suspend our mirrors just naturally vibrate at certain frequencies and overtones. So some of the peaks that you see there are just caused by the molecules in those glass fibers. We can't really do anything about those. The green stuff at the low end, those are some calibration tools that we use. So we can inject a signal into the interferometer. We know what we're injecting. We look at how the interferometer responds. And that helps us to calibrate the scale basically that we're looking at and to know that, to understand what we're seeing and what's coming out of the instrument. But we are locked in observing right now. Yeah, question?
Kim, if there was an event like you showed before, different major events, where would you see that? And would the operator look at that and say, that you had said before, there's like a few minutes where the signal is analyzed and then you're passing it on to other, your partners. Like where in that bank of videos would you see something? Or would
we haven't had anything big enough, I think, that we would see visually. If you could, and maybe this relates to, I forget who asked the question earlier about if something like this happened much closer, what would it look like? You would, because the signal is
No, I meant seeing it right there, like the data coming out from the from the instrument.
Yeah, that's what I'm
Is there-
talking about. So you would potentially see like a blip moving from the low frequency to the high frequency as the signal moved through the instrument, or as the instrument responded to the wave. You would have to be something really close and really big for us to visually see that. But you see, there's like a lot of schmutz around there, so it kind of conceals those finer visual cues. And that's where obviously our computing analysis comes in, where it can pull out and extract just the gravitational wave data out of this mess of other noise sources.
Slightly more on that.
Oh, Ibrahim has something to contribute.
So slightly more on that, it would be a bit it would be a bit difficult to catch the gravitational wave happen as it comes in, because the degree of the order of magnitude to which it happens, if you look at the y-axis that was on there, if you recall it, it was going down. Each sort of block is an entire order of magnitude. So since gravitational waves in general happen on the degree of a 10,000th of a proton, the waves would need to, in order for you to just see it, would need to be at least one entire order of magnitude in like magnitude in order for you to properly actually visually see it. In terms of what's noticeable, other than the fact that this thing updates every like 1 second.
Yeah, right. That's true.
To see it, like, let's say it was like fully like real time, you might be able to catch it if it was really, really, really big. But even then, it would need to be like a third or a quarter of magnitude.
Okay.
And you need to know where it happens. For one of the last like huge candidates that happened, I do recall there was some talk about how if you really zoom in, like, and I mean, don't just take this graph, but you properly like zoom in and you know where to look, then yeah, it was sort of visible in that area.
Oh, okay. That's cool. All right, cool. See, I'm learning something too. That's cool. Thank you for the question.
But well, just to follow up on that, if you had an event, I mean, what happens? Does a bell go off, or do you have to sift through the data to find the event?
Yeah, so that's a great question. So an event happens, right? I sit here, the robot on my left goes super event, and then the sort of the name of the event, and that's related to the GPS time and the year and the category that the event is in. So for example, a super event is an event that was caught by all detectors that are currently live. So that means that at that amount of time, the Livingston detector, the Hanford detector, and either Virgo or Kager, whichever one was up at that time, if that caught it, that's a super event. I'm now then not allowed to touch anything for 30 minutes, because this is like the start of like clean data time. Immediately, a notice goes out to the LIGO collaboration, all like 90-something universities. What happens then is there's a live discussion on one of the one of the sort of like channels, kind of like Slack channels, and they're actively talking. These are like people who are like supposedly signing off. The reason why it's 24/7 is that, you know, the sun never sets on the LIGO
Empire.
So someone is always awake to do this stuff, and it is very much like planned out like that, where there's a rapid response team, and then they know exactly what to accept it if there aren't like fringe, oh, there was a data glitch around this time, or oh, there was a, then it goes one rung higher. Oh, maybe there's data glitch. Is that okay? Then the next sort of like detection specialist like goes on and like signs off on that. After that discussion, then it's given out. Meanwhile, I also get a phone call saying super event, like this and this happened, and the standoff live goes on, and I'm not allowed to touch anything. Those are only for the ones that the automation was able to catch, the ones that the pipeline goes in. After all of that happens, then there's like a way more sort of in-depth parsing of the data to see if there were any other candidate events. And so, yeah, it's like a whole like live thing within like, for certain events too, like very high profile ones, entire telescopes will like spin and look at that area depending on if the sky localization is good. For example, the sky localization is like, so it's like if you have two detectors, the most that you can detect with that in terms of where it is in the sky is like a strip, right? And much like how triangulation and that kind of stuff works, where it's like the more that you have like a detection, the more that you can like pinpoint the geometry of where that thing is. For some detections, it's easier than others depending on the plane of where the two black holes might have collided, stuff like that. So if it's a particularly lucky geometry that we have and we can detect like where like where in the sky this happened, then the pipeline extends its way out to other sort of like astronomical sources. So the idea is that like if LIGO can hear a thing and an observatory can see a thing, then you can really connect those senses, like sort of get a sense of like that qualia between the two, like having like we saw the thing and now we can hear the same thing, and that would be great sort of physics. One such example of those is binary neutron star mergers. So neutron stars are very bright. They're not like black holes, and they're also very big in the section of now that we can like detect them. And so if a detectable binary neutron star is detected here, that is a very like high profile sort of event that we would definitely, the pipeline would go out to automatically spin some telescopes on Earth in order to look at that. Because if you can see that happen and also feel its gravitational perturbations here on Earth, that is a huge like way for the unification of these two fields. One, which the sensing mechanisms are in so far like they're totally unrelated so far, you know. And that's why it's like a new field of detection measurement, etc.
Awesome. Yeah, I spent a bit of time talking about the neutron star merger and like all the crazy science that came out of that. So, but we only have one so far. There's a lot of questions, you know, people are asking, how come that's the only one we have right now? So, yeah, the astronomers are kind of grappling with, you know, what do we know about populations and why aren't we seeing more of these things? So, I'll show you one more graph in here, and then, you know, you guys probably want to go to sleep. This is, again, something I think you can see online eventually. Again, I'll send you the links to it. But this is just a way that we monitor our range. And I'm going to lift the camera up a little bit. So the blue line up there is the signal coming from Livingston in Louisiana. The red line is Hanford. And then in the lower graph, the purple line is Virgo in Italy. And the vertical scale is in megaparsecs. And so this is what I was saying earlier, where we use a neutron star merger as kind of our baseline to estimate how sensitive we are, given that neutron star mergers are going to be kind of the least powerful, you know, faintest things that we could detect. How far away could we detect the least faintest thing? Black holes are, mergers are detectable much farther out. And so we use neutron star mergers as kind of a ballpark of how sensitive are the instruments. And so right now, looking at the charts, Hanford, we're operating at around 160 megaparsecs, and Livingston's kind of up around 170 megaparsecs. Actually, they're not online at this precise moment, but in the last 24 hours, they were kind of around 170. There are differences in, you know, environmentally, other differences that account for why the sensitivity of the detectors varies. But that means that theoretically, we could detect neutron star merger 160 megaparsecs away. So, you know, 500 billion light years, something like that. And that just gives us a good sense of how well are we performing.
All right. Well, thank you, Kim. This has been a terrific virtual tour. And
oh, good. I'm glad you liked it. I had to, you know, improvise a little bit with the camera, but hopefully we hit the high spots that we normally send, you know, take our visitors on site to. So.
All right. Well, once again, thank you so much.
You are so welcome. And again, please, you know, send any additional questions my way. I'm happy to answer or, you know, get some answers for you. We're always eager to, we're still pretty new at this. So questions are really valuable to us, and how people in the public kind of interpret what we do and the questions that they have. So for all of us and, you know, and our outreach team, it's always great. So don't hesitate to ask us or send us any questions. And please come visit us. Or if you're in Louisiana, you can visit the Louisiana facility. They also do public observing days. So yeah, a couple of opportunities to do that if you get a chance.